Okay, so today we're going to be talking about isotopes, what makes them different from one another, and also what makes them important and some of the things about them. So isotopes, the first thing we should do is define what this is. So an isotope is a version of an element that has a different mass. So when you're looking at the periodic table, there are 118 elements. Every single one of those elements, or almost all of those elements, have more than one version, and those versions will have different masses from one another. So one example of this would be like carbon. Carbon, there are actually 3 isotopes that we know about. There's carbon-12, carbon-13, and carbon-14. Now, all 3 of these isotopes have the same atomic number because they are all carbon. So pause the video, look up carbon on the periodic table. Carbon has a total of 6 for its atomic number, so it has 6 protons. So when you are counting the particles for these atoms, the number of protons will be 6 for all of them because all 3 of these are carbon and have an atomic number of 6. However, the mass numbers are all going to be different. And if you remember from last week when we were learning about how to count atomic particles, the mass is the number of protons plus the number of neutrons. So if the protons is going to be the same between all of the elements, that means the neutrons is going to be what is changing. Our first atom has a total of 6 neutrons because my mass number is 12, and I know that 6 plus 6 is 12. My second isotope has 7 neutrons because they have to add to 13. And my third isotope has 8 neutrons because it has to add to 14. All 3 of these are neutral, so they're all going to have 6 electrons. Okay, so when you are looking at different isotopes of an atom, really the only difference between them is the number of neutrons that they have. So that's actually pretty important. Let's write that off to the side. The only difference between isotopes is the number of neutrons they have. Now we know that neutrons are neutral, and they don't really have that much of an impact on how these chemicals react. Because they're neutral, really their only purpose is just to add mass to the nucleus of the atom. So because of that, all of the isotopes of an element are generally going to behave in a very similar fashion. They will undergo the same chemical reactions. They will generally look the same. The only real difference is their mass, their weight. Carbon in particular has 3 isotopes. Carbon-12 is the most common by far. I don't have the exact percentages, but I know it's over 95% of all carbon atoms. Carbon-13 is pretty rare. And then carbon-14 is actually radioactive, which means it breaks down. You can sometimes see this with isotopes. After you add a certain number of neutrons, they start to become unstable. That doesn't mean they don't exist, but it means they can sometimes break down. Radioactivity is not necessarily a bad or a dangerous thing. Radioactivity has a bad rep. There are certainly some cases of dangerous radioactivity, but carbon is very safe and very normal. So carbon 14 is actually very useful because the fact that it's radioactive and the fact that carbon is one of the most common elements in nature means that we can do something called carbon dating. So you might have heard of this before. But basically, because we know the rate at which carbon breaks down, the half-life of carbon 14 is like 6,000 years or somewhere around there. If you look within a substance and see how much of the carbon remaining in it is carbon 14, you can figure out how old that substance is. So carbon dating is really useful because of that. We can date things up to 6,000 years old. Past that, you have to move to a different isotope of a different element. Usually, I think uranium is used past 6,000 years old. But up until then, you can age something with carbon 14 dating. You can figure out how old it is. Okay, so like I said before, carbon 12 is the most common form of carbon. This is actually reflected in the atomic mass. So if you look up on the periodic table, carbon's box will look something like this. And of course, all periodic tables are laid out slightly differently, but you usually have the atomic number somewhere in there, the symbol. Sometimes if the periodic table is nice, the name will be given to you. And then at the bottom, there is going to be a number. That number is what's called the average atomic mass. Now, the average atomic mass is not going to be the straight average of those three numbers. If you take the average of 12, 13, and 14, you do not get 12.011, you get 13. The average atomic mass is actually a weighted average. Let's talk about what that is. And you might already know. But a weighted average is an average that takes the abundance of the different parts into consideration. So if one of the isotopes is much more common, it's going to have a heavier impact on the average. So it is an average that takes the abundance into consideration. Okay, this is actually something that you can calculate pretty easy. So the rest of this lesson is mostly going to be talking about how to find a weighted average of something. But one nice thing about weighted averages is that if you have a periodic table that you can look the mass of an element up on, you can use that atomic mass to figure out which of the isotopes is the most common. So if you look at carbon's atomic mass on the periodic table is 12.011, which of course is very, very close to the number 12. It's a little bit higher than 12, but not by much. Because this average is so close to the number 12, that tells us that carbon 12 is the most common isotope. It is raised a little bit above 12 because we have to take carbon 13 and carbon 14 into consideration. But because those two isotopes of carbon are so rare / radioactive and not even existing forever, they don't really impact the average very much at all. So another thing this tells you is that if you had a sample of carbon and you were to weigh that sample of carbon, it would have a weight of about 12.011 grams if you had 1 mole of it. This is useful to us because usually when we're dealing with chemicals, we're not dealing with pure isotopes. Usually we have a blend of the different isotopes. So the average atomic mass is going to tell you what the weight of the average blend of isotopes is, rather than just telling us the weight of one particular isotope. Okay, so how do we calculate this? Well, in order to calculate the weighted average of a set of isotopes, you need two pieces of information. You're going to need the exact weights of the isotopes. In a pinch, if it's not given to you, you can use the mass number. So you can use 12 for carbon 12, 13 for carbon 13, and 14 for carbon 14. But it's not going to give you as accurate of a result because those are not exact weights. Those are kind of like the rounded weights. So if you have the exact weights of the isotopes, that's better. What you also need is the percent abundance. And the percent abundance is just the percent of all atoms of that element that exist as that isotope. So it's telling you what percent of carbon is carbon 12, for example. So what percent of all atoms exist as that isotope? Oh my gosh. Okay. So I'm going to go ahead and write down the formula for calculating the average atomic mass, and then I'll explain it after I've written it down. So average mass is equal to F1 M1 plus F2 M2 plus F3 M3 for however many isotopes you have. So I have it written out here for 3 isotopes. If you had fewer than 3, then you wouldn't have to go all the way out to 3. If you had more than 3, then you would continue this equation for however many you actually had. So when you are looking at this equation, average mass is the mass, that was on my eraser. Average mass is the mass from the periodic table. Actually, I'm going to change colors. I have all these pretty colors, like let's use them. So average mass is the mass from the periodic table. And of course, it is the average mass for that element. F, this is the fractional abundance, and I'll talk about what that is in a second. And then M is the mass of that element. Of that isotope. Sorry, I said the wrong thing. Okay. So what is fractional abundance and what makes it different from percent abundance? Well, percent abundance is of course going to be a percentage. So percent abundance might be something like 75% and 25%. So say I had 2 elements. I had X13 and X15. First of all, when you're looking at your percent abundances, one thing that you should notice about them is that when you add them, you always should get 100% for all of your isotopes. And that's because a percent is telling you a part of a whole. And if you add up all the different parts of a whole, you get a whole. So all of your percentages should add up to 100%. If I know that one isotope is 75% of all atoms, and I know that there's only 2 isotopes, that means the other one has to be 25% of all atoms. The math doesn't really make sense if that's not the case. Fractional abundance is just that percentage in decimal form. So what you do to take a percentage and make it into decimal form is you just divide it by 100 or move the decimal over twice. Fractional abundance is usually how percentages are used in real life. When you are taking the percent of something, usually this is what you plug into your calculator. So if you want to know what 75% of $13 is, you'll take 13 and multiply it by 0.75. And that tells you what 75% is. So the fractional abundance is what actually goes into the equation. The percent abundance is usually what's given to you because those numbers are just a little bit nicer to look at. And of course, the fractional abundances are always going to add, if you see this, to 1. So that's kind of nice too. All right, so let's go ahead and do a practice problem so that you can see how this is done. So I already have one ready. This problem says use the atomic masses of each of the 2 isotopes of chlorine, along with their percent abundances, to calculate the average atomic mass of chlorine. Chlorine-35 has an atomic mass of 34.969 AMU, so that's the exact mass. I'm going to highlight that. And percent abundance of 75.77%. And chlorine-37 has an atomic mass of 36, that should not be a comma there, 0.966 AMU, and a percent abundance of 74.23. So you can see the first one, this is for chlorine-35, and it is the exact mass. So you can see why using the exact mass is better. In a pinch, like I said before, you can use the mass number. If you were to use 35 instead of 34.969, it wouldn't really change your answer all that much. But to be on the safe side, if the exact mass is given to you, then go ahead and use that. Okay, so I have 2 isotopes. I have chlorine-35 and I have chlorine-37. And those are the 2 versions of chlorine that exist. Chlorine-36 is not really stable for complicated physics reasons. So chlorine-36 just, it doesn't exist. But chlorine-35 and 37 are both okay. So chlorine-35 has a mass of 34.969 atomic mass units. And chlorine-37 has a mass of 36.966 atomic mass units. I'm just organizing my information right now. Chlorine-35 has a percent abundance of 75.77. When I'm calculating the average atomic mass, I do want to use the fractional abundance instead of the percent abundance. So what I'm going to do is actually move that decimal over twice. You get 0.7577. And there's no unit for percentages. It's just alone. And then for this one, it'd be 0.2423. And if you were to double check and add both of those percentages together, you should get 1. Because when you add all of the percent abundances, you get 100. So when you add all the fractional abundances, you'll get 1. Just a quick thing you can double check to make sure everything is like ready to work out. Okay, so average atomic mass. Let's change colors. Let's do red. Let me just write down the formula first. So first of all, I only have 2 isotopes for this problem, so this one's not too bad. F1, M1 plus F2, M2. I only have to go out to the second term in the equation because I only have 2 isotopes. The fractional abundance is going to go here. The mass is going to go here. fractional abundance, mass. So I just have to plug those numbers into the equation. So you get, I like to use parentheses for multiplication just because I think it's cleaner. 0.7577 times 34.969. And then the other term is 0.2423 times 36.966. Okay? So now what I'm going to do is multiply those together. You will need a calculator for this. Please don't try to do this in your head. 0.7577 times 34.969 is 26 point, let's see, I want that. And then I'll talk about sig figs in just a second. The unit will be atomic mass units. And then the other one, 0.2423 times 36.966 is 8.9568618. Okay, so I just multiplied those parentheses together. So before we move on to the last step, let's keep track of significant figures. You always want to keep track of sig figs in every step of the math that you do. So remember, for significant figures, when you are multiplying two numbers together, it's the number of significant figures that you care about. Our first number here, 0.7577, had 4 sig figs, and we multiplied that by something that had 5 sig figs. For the first one, remember that beginning 0, you never count beginning zeros. So you can just pretend it doesn't exist and just count from the 7 on. So that means my final answer should have 4 sig figs. 1, 2, 3, 4. I'm not actually going to round it, but I will write down which of the digits are significant. So you can do that by underlining them. You can do it by underlining just the last one. Oops, I just erased my 2. Let's fix that. That's usually what I do. I like to underline just the last significant figure, or where the last significant digit is. So basically everything that comes after that 9 is not considered a sig fig. I'm just writing it down so I don't accidentally change what my answer is by rounding it. Okay. The next one is going to be the same. This is 4 sig figs. This is 5 sig figs. So this should have 4 sig figs, which would be this 6. All right, so the last thing I have to do now is just add those two numbers together. So 26.496013, put the whole number in your calculator, plus 8.9568618. And you get that the average atomic mass is equal to 35.452871. Of course, we have to round this for sig figs, so let's think about that for a second. I got that number by adding. The rule for adding and subtracting is that you look at where the last significant figure is, and that tells you where to round your number. So for our first number that we added, the 26.4960113, the last significant figure was that 9 that is underlined. So that's going to be 2 decimal places. For the second number, that 6 is 3 decimal places in. So that means my final answer should only go out to 2 decimal places. So I'm going to round it there where that 5 is. And that'll be my final answer that I report. Okay? So not too bad. I went through it kind of slowly and I wrote out all of the steps, but once you do a few of these problems, you're not going to have to write out just as much as I did for this one. So here I wrote out everything, but you're not going to have to do that once you get good at these. So when you are working on practice assignments or quizzes or anything, make sure you show as much work as you can so that if something goes sideways, I can figure out exactly where and give you the help that you need. All right, well, that's it for isotopes. Hope you guys enjoyed this video. Goodbye.